Hello everyone, today I'm going to introduce you arithmetic coding. Arithmetic coding is a form of entropy encoding used in lossless data compression. Normally, a string of characters is represented using a fixed number of bits per character. When a string is converted to arithmetic code encoding, frequently used character will be stored with fewer bits, and not so frequently occurring characters will be stored with more bits, resulting in fewer bits used in total. Arithmetic coding, different from other forms of entropy encoding such as Huffman coding, is that rather than separating the input into component symbols and replacing each with a code, arithmetic coding encodes the entire message into a single number, an arbitrary position fraction q, where q in the range of 0.0 to 1.0. It represents the current information as a range defined by two numbers. Later, I will use an example to illustrate to you what does this mean. Suppose we gave a code book X with 0, 1, and 2. And their probability is representatively 0.2, 0.4, and 0.4. And the message going to be encoded is 210. Suppose there is an interval from 0.0 to 0.1. Now our message is 210, which means that we divide this interval according to the possibility, which is for 0 chunk, it is 0.2. And for 1 chunk, the length is also 0.2, so here is 0.6, and the final chunk is 2. The first message code word is 2, so we divide this 2 chunk according to the same ratio like before, which is 0.2 and 0.4 and 0.4, which is 0, 1, 2. And then the message is 1, so we divide this 1 chunk like the same message before, 0.2, 0.4, 0, 1, 2. So the last message is 0, and the purple chunk is our message chunk. The lower bound is A and the higher bound is B. Now we defined C0 equals 0, Cj equals P0 to a sum of P0 to Pj minus 1 for j equals 1 to n. And Dj equals Cj plus Pj for j equals 0 to n. In the interval, we can get the Cj, which is equals to 0.0, and C1 equals 0.2, and C2 equals 0.6. For D0 equals 0.2, D1 equals 0.6, and D2 equals 0.1. The C and D is used to define A and B, which means the lower and upper bound of the chunk, the message chunk. The C is used to define A in each iteration, and D is used to define B in each iteration. What does it mean? In detail, I will demonstrate you. Let's make a table. A, B, and W. W equals to B minus A. This is as our first column. Suppose the initial A is 0.0 and initial B is 0.1, which means that W is B minus A, which is 1. And when we receive the first message, which is 2 in this scenario, we update A with this formula. A equals A plus W times Cj. The J means the index number in the code book. Our code book is 0, 1, 2, and since we receive a 2, the index of the code book is also 2. This is just a coincidence. If you use some other code books like A, B, C, you have to decide the J number by the index. And let's get back to calculation. A, which is A plus Wj, which equals 0.0, 1.0 times Cj, which is C2, is can see that it's 0.6. So the updated one is 0.6. 0.6. And we calculate the B with this formula, A plus W times Dj, which is equal to 0.0 plus 1.0 times Dj, which is D2 equals 1. So the updated B is also 1. And the new W is 1 minus 0.6, which is 0.4. Then go to the next message, which is 1. The updated one is 0.6 times plus 0.4 times C1, which is 0.2. Is equal to 0.68. And the B is 0.6, which is A, times 0.4 is W, times D1, which is 0.6. This equals to 0.84. And the updated W is 0.16. Then we come to the last message, 0.68 times 0.16 times C0, which is also 0. So the updated A is 0.68. And the B is 0.68, which is A, times 0.16, which is W, times D0. And the D0 is 0.2. So the updated B is 0.712. Which means that this purple chunk, which represents the encode, is between 0.68 to 0.712. Since we get this message chunk equals 0.68 to 0.712, we will then translate this message chunk from decimal into binary, and use a technique called rescaling to get our final encoded message. How does this work? I will demonstrate you. Let's divide this 0.0 to 0.1 interval into binary, which is consist of 1 chunk and 0 chunk. And we can see that our message chunk is contained in this 1 chunk. So we rescale this 1 chunk and let 0.5 as the lower bound and the 1 as the upper bound. 0.5, and we divide this chunk again, which is 1, 0, and 1, 1. And this number equals 0.5 times 1 over 2 square, which is equal to 0.75. And we can see that this message chunk is now in this 1, 0 chunk. So we rescale this 1, 0 chunk. Let the 0.75 as the upper bound, 0.75 and 0.5. And we divide it, it's 1, 0, 0 and 1, 0, 1. And this number is 0.625. And we can see, we can observe that the message chunk is in this 101 chunk. So we rescale this 101 chunk again. Yep. And divide it 1, 0, 1, 0, 1, 0, 1, 1. This is 0.75, 0.625. And this number is equals to 0.625 times 1 over 2, which is equals to 0.6875. Now we can observe that the message chunk, which is 0.68 and 0.712, which have the middle value of this chunk, of this interval in between. So we divide this one into 4 1, which equals to 0 into 4 into 1. And this value equals to 0.6562625 times, and this value equals to 0.71875. This means that our message chunk is between these two chunks. So we rescale this 2 chunk again. We let the this 0.71875 as the upper bound and 0.65625 as the lower. And we can calculate this value equals to 0.562 times 0.67185. And we get this value. And we can see that our chunk is 0.68 and to 0.712. And this 10110 chunk is in our message chunk. So we let this first chunk that's in our message chunk as our final encode word, encode message. Encode 210 as 101100. Now we are changing the algorithm I demonstrated before into the Python code. First name a class, and this is the infinite precision version. The user need to provide a frequency table of the codebook in the codebook, and it will use the get function to get the frequency table into probability table. And here comes the encoding code part. The user give the message string, and it will change into a message list. And here is the p, which according to the probability tables value, such as the 0.2 for 0, 0.4 for 1, and 0.4 for 2. And then we define the C. As I have defined in the algorithm, C0 is equals 0, and Cj is the sum of Pj, P0 to Pj for the definition of D. And in infinite precision, we initiate the A and B as 0.0 and 1.0. Then we traverse all the message in the message list, and for example 1, 2, 1, 0, and we use this function to update the new A and B, and when we get the encoded message chunk, which is A to B, in the example is 0.6 to 0.712, we use the A and B to translate them into the binary form, the decimal interval to the binary. And here is the condition that it's only divided into two sections. And after that, if we use if it's in the circumstance that the middle value is bigger than the A and smaller than the B, it will need to be divided into 4 sections. And since it has the middle value in between, so there is only two possibilities, which is 0, 1, 1, 1, which has 0, 1, and the other is the one that's plus 1. It is 1, 0, 0, 0 with S0. It has only these two possibilities. Above is the encoder part, and here comes the decoder part. The first thing we need to do is to translate the encoded message into Z, which is into decimal, and I use the function from the internet that change the binary into decimal, binary fractions into decimal, and the same for the initialization of A, B, and P, and things for the definite C and D. And there is a while loop, which is always true. In the while loop, we decide the Z is in which chunk, and then we emit that chunk message, and then up go to that chunk so that we can get the second iterations, get the second iteration chunk. And when we meet when the chunk equals to the end of value number, we return to the decoded message. And here is the test of my Python code, and I will run it. The original message is 210, as we have used in the algorithm. And we can see that we get the encoded message is 101100, which is also the same as the algorithm. And here we can also get the decoded. In arithmetic coding, in order to ensure the decodability of the encoded message, we have 2 ways. First, we can encode the length of the original message, such as in this example, the encoded message is beta 1 to beta m, and the original message is beta 1 to beta little m, and we can encode the length of the original message m to tell which part belong to the original message and which part belong to the next message. And also we can use the end of file symbol. For example, we can use 0 as our example's end of file symbols, and we can get the minimum I that was in this message chunk A and B, and then we can use the property of the prefix code to tell the little m and to tell what is the original message and what is the next message. And another property of the arithmetic coding is the precision. The above explanation of arithmetic coding contains some simplification. In particular, they are written as if the encoder first calculated the fractions representing the endpoints of the interval in full using infinite precision, and only converted to the fraction to its final forms at the end of the encoding. Rather than try to simulate infinite precision, most arithmetic coders instead operate at a fixed limit of precision, which they know the decoder will be able to match, and round the calculated fractions to their nearest equivalence at that precision. The following code shows how this would work if the model called for the interval 0 to 1 to be divided into halves, and this was approximated with 8-bit precision. Here is the code. Let's talk about the finite arithmetic coding. Finite arithmetic encoding is quite similar to the infinite encoding, but there are one things which tell the difference. Is everything in finite precision is integer. Now I'm going to tell how can we do that. So we need to define the precision as the number of bits used to represent numbers. In this example, I choose 8. You can choose anything according to your examples. And we define the whole is the 2 power the precision. It was used as the initial value of the b, which is the upper bound of our chunk, and similar things as the definition of c and d. But how do we make the updated c to be integer? Now we have to give an R value. The R value is used to multiply the possibility value and make the fraction, the possibility fraction into an integer, so that the updated Cj value will be an integer. Same for the Dj value. And the algorithm is quite similar. They all use the rescaling, and the difference is when we updated the a and b value, in order to make sure it is integer, we use a function called round. And this functions to make sure that the updated lower bound and the upper bound of the chunk is an integer. And the same for the translation from the decimal into binary. We have two kind of division into half and the division into quarter. This is the division into quarter, and use the same append because of the middle value. And when we talk about the decode function, same, we need to define the position value, and also we need to initialize the z, and use the encoding message to get the z value, which is representing the chunk within the message chunk. This while loop is quite similar to the one that's in the infinite version. Firstly, for this for loop, it will decode next symbol and update the a and b value. And one thing we have to make sure that is to rescale at exactly the same times during the encoding as we did during the encoding. This is the quintessence of the decoding part. And the other part is quite similar, and the tag is in which chunk and emit the value. And this is the example I made to test my algorithm. And the original message is the 210. It's the same as the example. And we times the R value, which is used to make the probability integer. I choose 100 because it is 0.2 times 100 is 20, and 0.4 times 100 is 40. So to make it an integer, and we can run it, and the answer is the same. The final things I want to mention in this presentation is the pros of the arithmetic coding. First, it's near optimal even on very large message. Second, it's very fast, and the third is it's separating modeling from coding. Due to the time limit, I'm not going to dive into these materials. But if you are interested in these materials and their proof, you can click this link. It gives a very good proof of these three properties. Thank you.